Let's look at a special class of reactions known as oxidation reduction reactions, or redox for short. And you're actually, there's more examples of these reactions than some of the others, like acid-base or just a simple double exchange reactions. Iron rusting is a redox reaction. When iron comes into contact with oxygen, and especially if it's wet, water actually is a catalyst. It speeds up this reaction, but it's not necessarily required. When iron reacts with oxygen in the air, it makes rust, which is iron 3 oxide. And of course we would need to balance this equation as well. This is a redox equation. In a redox equation, electrons are transferred. Okay, and when you have electrons being transferred, what that means, that things are going to start off on the reactant side of the equation with one charge, and they're going to end up on the product side of the equation with a different charge. In a redox equation, you will have oxidation or in a redox reaction, I could say, and reduction. Oxidation is the loss of electrons, and electrons are a negative charge. So when you lose electrons, what that's going to make happen is your charge is going to go up, right? Because if you lose negatives, then your charge is going to become more positive. So we would say it goes up. And how we word that in chemistry, we say that there's an increase in the oxidation number. Think of an oxidation number kind of like a charge. Okay? In reduction, that's the gain of electrons. And if you gain electrons, if you gain negatives, then that's going to cause your charge to start going down. So we would define that as a decrease in oxidation number. And there's a little acronym that helps us remember this. LEOGR. What in the world? Lose electrons, oxidize. Gain electrons, reduce. Okay? So LEOGR will maybe help you keep that straight. Losing electrons is oxidation. Gaining electrons is reduction. Now, whenever you have redox, whenever you have something being oxidized, whenever you have one thing losing electrons, you have to have something gaining electrons. These always go hand in hand. If one thing's being oxidized, something else is going to be reduced, because you can't have electrons just flying out into nowhere. Something's got to gain them. So if we look at this equation, let me show you how the oxidation numbers are changing. And just follow along with me for now. In a second, I will go in and show you where I came up with these numbers. The oxidation number for iron on the reactant side of the equation is 0. The oxidation number for oxygen on the reactant side of the equation is 0. And when I look at the product, the rust, the iron 3 oxide, the oxidation number for iron here is +3, and oxygen here is -2. So once I've assigned oxidation numbers to every species in the reaction, I can then look at what was oxidized. Well, iron started out at 0, and it ended up at +3. So didn't its charge increase? Its number went up. Therefore, iron was oxidized. Now, oxygen started out at 0, and on the product side, it was -2. From a 0 to a -2, that went down. Therefore, oxygen was reduced. So in this example, we have one thing being oxidized and something else being reduced. Like I said, those always come in pairs. If you have one, you have to have the other. Now, how did I know those numbers? Where did I get the numbers, the 0s and the 3s and the 2s? Well, there are some rules for assigning oxidation numbers. And there are rules in your book for assigning oxidation numbers. I might give them to you a little bit differently than how your book has them worded, but it's the same rules. The first rule: for anything in its elemental form, the oxidation number is 0. Anything in its elemental form. That is how I knew, if we look back at the previous slide, iron, that's elemental iron. That's how I knew it was 0. Oxygen, that's elemental oxygen. Remember, there are some elements that are diatomic. So that's how I knew that iron and oxygen were 0. Okay, the second rule. For a monoatomic ion, the oxidation number equals the charge on the ion. Monoatomic means a single atom ion. When we learned to write ionic formulas, that's what we were dealing with, is monoatomic ions and swapping and dropping. Rule 2, that's how I knew that iron was +3. Where did the 3 on the oxygen come from? It came from the charge of the iron. Where did the -2 or the 2 on the iron come from? Came from the charge of the oxygen. Remember swapping and dropping? So all I've done for rule 2 is reverse that and gone back to what their charges were. Okay? And those same rules apply that we learned early on. Group 1, those like to be +1. So that's what their oxidation number. If they're by themselves, they're 0. If they're in a compound, their oxidation number is +1. Group 2, it can be either 0 if it's in its elemental form, but if it's in a compound, it's going to be +2. Aluminum is either going to be 0 or +3. Okay? When we look at things in a compound, the nonmetals, the halogens are typically -1. In an ionic compound, chalcogens are -2, etc. Hydrogen is sometimes pointed out special. The oxidation number for hydrogen is either +1 or +2. I'm sorry, I said +1 or +2. I meant +1 or -1. Anytime you have hydrogen with a metal, when hydrogen's with a metal, it's -1. Anytime it's with a nonmetal, hydrogen is +1. Okay, you're going to see oftentimes hydrogen with a nonmetal. Rarely are you going to see hydrogen with a metal. An example of that would be like sodium hydride. Okay, there's hydrogen with a metal. In that case, the hydrogen's -1. Hydrogen with a nonmetal, well, in water, for example. Okay, hydrogen's +1. In ammonia, because nitrogen's a nonmetal, hydrogen's +1. So more often you're going to see it with a nonmetal. Okay, another rule is that the sum of the oxidation numbers in a compound or ion always equals the overall charge. On the compound or ion. Okay, most of the time this rule is applied to ions, but it fits for compounds as well. Okay, let me show you what I'm talking about. If we go back to that example of iron Fe2O3, okay, forget the coefficient, y'all, because the coefficients have no bearing whatsoever on oxidation numbers. They're just there in the balanced equation, but they have no bearing on oxidation numbers. Do you see, if you're looking at rust, Fe2O3, there's 3 oxygens and each one has a -2 charge. 3 minus 2s gives you a -6, doesn't it? Do you see where I'm going? If there's 2 irons and each of them's +3, well, 2 plus 3s is a +6. So those add up to be a 0 overall charge. That's why we swapped and dropped way back in chapter 1 or chapter 2, is to give it a 0 charge. You knew rust would have a 0 charge because there's no charge written up here, so it had to have a 0 charge. So the same rule right here that we're about to apply to polyatomic ions, you've applied it on the simple monoatomic ones as well. For example, nitrate. Nitrate is NO3 with a negative charge. Nitrate is made up of 1 nitrogen and 3 oxygens, isn't it? There's an N and there's 3 O's. And what this number 4 tells me is that the sum of those, the N plus the 3 O's, it has to equal the overall charge. So it's the sum of those oxidation numbers has to equal -1. I got that from right here, this charge. Now, 9 times out of 10, what we know, if we're given like this one, nitrogen and oxygen, what we know is we know what the oxidation number for the oxygen is. Okay? Because oxygen, anytime it's combined with a nonmetal, it's always going to be -2. So, nitrogen plus, what did I say we know? We know that oxygen's -2. And I said anytime it's combined with a nonmetal. Anytime it's combined with a metal, it's -2. In this situation, it's also -2. Okay? What we've done here is we've set up an algebraic equation. We started out with N plus 3 O's equals -1. We had 2 variables, N and O. We know that O is -2 because 9 times out of 10, that's what O is. It's -2. Unless it's by itself, plain old oxygen, it's going to be 0. And there's a couple of other special exceptions as well. We plug in the -2 for the O and we solve for N. So if we follow through, N minus 6 is equal to -1, and we add 6 to both sides, we see that N is +5. That is the oxidation number for the nitrogen in this example, +5. Let me work one more example of polyatomic ion. This time let's do sulfate. I want you to pause the video and solve for the oxidation number of sulfur in sulfate. Sulfur plus 4 oxygens is equal to -2. It's S and O. I have 2 variables. I have to know one. We know the oxygen. S is equal to +6. Okay, let's do one more equation. Let me tell you what we're going to react. And you write the balanced equation. And then assign oxidation numbers. Tell me what was oxidized and what was reduced. Let's take zinc metal and put it in hydrochloric acid. Zinc metal and hydrochloric acid, those are your reactants. So pause and write those reactants. And see if you get this. Hopefully you did. The products of this reaction are going to be zinc chloride and hydrogen gas. Pause, right? And hopefully now you've just restarted it and you're checking zinc chloride and hydrogen gas. While it was paused, did you remember to balance it? Balancing is not going to have any bearing on the oxidation numbers, but we do need to balance the equation. Now assign oxidation numbers. Use those rules we just went over and assign oxidation numbers. The zinc and the hydrogen are really easy because they're elemental, they're by themselves. The others might take me a second because I have to go back and reverse that swapping and dropping. Those are my oxidation numbers. If you look carefully, you'll see that chlorine started out -1 over here and it ended up -1 over here. So nothing happened to the chlorine. It wasn't oxidized or reduced. What happened to zinc? Zinc was oxidized because it started at 0 and it ended up at +2. What happened to hydrogen? Hydrogen is reduced because it started at +1 and ended up at 0. Now, zinc was oxidized. Whatever is oxidized is known as the reducing agent. Because it's the agent, it's the substance that helps something be reduced. Whatever is reduced is known as the oxidizing agent. Because it's the substance that helped, in this example, it helped zinc be oxidized. So a lot of people think oxidation and reduction is confusing. Remember Leo Ger. Lose electrons oxidized. Whatever is oxidized is the reducing agent. Gain electrons reduced. Whatever is reduced, that is your oxidizing agent.